Hello, everyone. Welcome to today's webinar on selection and certification. My name is Zehra Şümer Yılmaz, and I'm the notified body and laboratory manager of USP Laboratory. As you saw in the webinar announcement, we are going to present this webinar with Mr. Emre Metin. If I were to talk a little bit about who we are, USP certification was established in 1998, is headquartered in Izmir, and is a leading organization in its sector with nearly 30 years of experience operating in the field of certification services in Turkey and internationally. USP certification, besides being an integrated organization consisting of a laboratory and notified body located in Istanbul, certification services in the culture, food and consumer products, textile and recycling, industrial certification, and management systems, as well as audit services in brand audits, second-party audits, and more. Together, we have national and international accreditations, wide representative networks, expert staff, and solution partners, our customers, and support their sustainability. We are expanding our presence in the sector with offices and operations in more than 10 countries, including Izmir and Istanbul in Turkey, as well as China, India, Bangladesh, Pakistan, Morocco, Cyprus, United Kingdom, and Italy. If I were to talk a little bit operations of our laboratory, we have an integrated structure as a laboratory and notified body located in Istanbul, as I mentioned before. Our laboratory performs a wide range of physical and chemical tests, primarily for personal protective equipment, including hand, food, and body protectors. In addition to general textile and leather and plastic tests, we conduct specialized tests such as shoe-to impact tests or glove impact tests and more. We also carry out UV aging tests on various products made of plastic, metal, and textiles. And ROS testing is also included in our scope. Beyond certification services, we are actively involved in many R&D research and development projects within the industry. Our laboratory is accredited for more than 50 parameters and can perform. Over to Mr. Emre Metin for a detailed explanation of the subject. Thank you.
Thank you, Eşim. And hello, everyone. We will conduct our webinar in English today, but we have some Turkish participants over the Turkey, but we will continue in English together. And I would like to welcome to what I believe is one of the most important technical webinar you will attend this year. It's Emre Metin. I'm electrical engineer and technical director in USB certification. And also I'm speaking to you from Istanbul, our laboratory. Today, we are diving deep into protection against electric arc standards in clothing selection and certification. Now, I know what some of you might be thinking, another PPE presentation, but I want to be clear from the start, this isn't just about compliance checkboxes or purchasing decisions. What we are discussing today is literally about the difference between workers going home safely to their families or not going to home at all. In my years working with electrical safety standards and certification, I have seen the aftermath of arc flash incidents. I have reviewed accident reports, spoken with survivors, and working with companies devastated by preventable tragedies. Every single statistic we'll discuss today represent real people, engineers, technicians, maintenance workers who thought they were taking reasonable precautions, but didn't fully understand the invisible forces they were working with. Before we begin our technical journey, let me set some expectations. We have about 40 minutes of core content ahead of us, followed by Q&A session. I encourage you to take notes, but more importantly, I want you to think about how this applies to your specific work environment. At the end of this session, you'll receive the PDF slides, and also we will put the video on YouTube. But the real value will be in understanding the principles behind the requirements. So let's get started with understanding what we are actually dealing with when we talk about the arc flash. And I will share with you the webinar agenda going back to slides, and we will go through the agenda. Let me walk our roadmap today. We are structured this webinar around 4 critical knowledge areas, each building one of the previous one. First, we'll establish the foundation by understanding arc flash hazards themselves. This isn't just a theory. We need to understand the physics of what happens during an electrical explosion to make informed protection decisions. We'll look at the multiple hazards involved, common triggers, and the real consequences of these incidents. Second, we will dive into arc flash analysis. This is my main expertise area, and I am doing also the arc flash analysis with the ATAP and also Big Silent programs. And the engineering methodology that transforms what might happen into what will happen with specific energy levels. This is where we use standards like IEEE 1584 to calculate the exact hazards at specific locations in electrical systems. This is the just only calculation methodology in the global. Also, we have ISE and also EN regulations and also standards to calculate short circuits in the ampere side, but globally we will use the methodology IEEE standards. Third, we will navigate the global regulatory landscape comparing NFPA 78E and IEC 61482 approaches. This is the main differences of the global approaches to put the logo and also the claims on the arc flash suites and also the other arc flash components. Understanding these differences is crucial for anyone working with international operations or equipment. Finally, we will get practical, discussing technical textiles, testing methods, proper selection, care, and maintenance of protective clothing that we use in the technical files also. Plus, we will share with you, with our expertise, the sustainability considerations, reuse, recycle, and also reclaim the materials in the technical textiles. Each section includes real-world applications and case studies. Our goal is that you leave with actionable knowledge, not just theoretical understanding. Yes, we will dive into physics of the electrical explosions. Now, let's get into the heart of the technical content. Understanding arc flash protection begins with understanding what we are protecting against. This isn't optional background, it's fundamental to making informed decisions. An arc flash is a low impedance connection through air that creates what we create the cold and electrical explosions. Maybe we can say it's a short circuit in the electrical engineering areas. But let me be very specific about what this means in practical terms. When electrical currents finds an unintended path through air, whether from equipment failure, human error, or environmental conditions, especially for the human error, we will look into this presentation. After this short circuit, it ionizes the air molecules, creating a plasma channel. This plasma conducts electricity while simultaneously reaching temperatures of 20,000 degrees Celsius. To put this in perspective, that's 4 times hotter than the surface of the sun. We are literally creating a miniature star inside electrical equipment. But here's what makes this particularly dangerous. This isn't a sustained process like a furnace or welding arc. An arc flash releases this energy almost instantaneously, typically lasting anywhere from a few milliseconds to several hundred milliseconds, depending on how quickly protective devices operate. The diagram you see here illustrates the multiple energy release mechanisms. We have copper vapor expanding by 67,000 times its original volume. We have molten metal droplets ejected at high velocity. We have intense light across the entire spectrum, from infrared through visible light to ultraviolet. We have pressure waves traveling at acoustic velocities. This is why I use the phrase forces of nature contained within a metal box. When that containment fails, when arc flash occurs, we are dealing with the physics that can replicate solar conditions in industrial environments. The key insight here is that arc flash isn't just a big spark. It's a complex, multi-physics event that attacks the human body through multiple mechanisms simultaneously. We will deep into how to calculate the arc flash explosion in the further slides. More than just heat. This brings us a critical understanding. Arc flash creates multiple hazards that attack simultaneously. Let me walk through each one, because understanding these individual components is essential for understanding why our protection strategies need to be comprehensive. Intense heat. The thermal energy from arc flash causes what we call thermal burns, but these aren't like burns from touching a hot surface. The energy transfer is so rapid and intense that it can cause second and third degree burns instantly, even through clothing. The energy doesn't just burn the surface, it penetrates deep into the tissue. Arc blast. This is often the least understood hazard, but it can be the most immediately dangerous. The rapid heating of air creates a pressure wave, essentially an explosion that can generate pressures exceeding 2,000 pounds per square foot. We are calculating with pounds. Most of the calculation methodology depends the pounds and also the US measurements values. These blasts can collapse lungs, rupture eardrums, and propel objects at speeds exceeding 300 meters per second. I have seen cases where the blast pressure threw workers across rooms or draw metal fragments through safety glasses. We call it arc blast. Intense light. The light from the arc flash spans the entire electromagnetic spectrum. The infrared radiation contributes to thermal injuries, while ultraviolet radiation can cause what's essentially a severe sunburn to exposed skin and permanent retinal damage. Workers have been blinded by arc flashes. They weren't even directly looking at the reflected light alone can cause permanent eye damage. Sound blast. Sound levels typically exceed 140 decibels, which is well above the threshold for immediate hearing damage. But it's not just the volume, it is the suddenness. The acoustic shock can cause immediate hearing loss and disorientation at exactly the moment when clear thinking is most critical. If you can't hear, you cannot move. The photograph here shows the violence of an arc flash test. Notice the massive fireball, the shower of molten metal, the bright light that overwhelms the camera despite protective filtering. Now, imagine being 3 feet away from this event while wearing inadequate protection. This is why I say arc flash attacks every sense simultaneously. A single creates thermal, mechanical, optical, and acoustic hazards that must all be addressed in our protection strategy. What causes an arc flash? Understanding causation is crucial for two reasons: prevention and risk assessment. Let me walk through the most common causes because each one has different implications for protection requirements. Equipment failure. This includes insulation breakdown due to age, moisture, contamination, or manufacturing defects. Equipment failures often occur with little warning and create very high energy arc flash events because the fault current may be limited only by upstream overcurrent protection devices. We call it the protection devices is the overcurrent, not overvoltage. These events are particularly dangerous because they often happen during normal operation when workers aren't expecting a hazard. Human error. This is unfortunately common and includes actions like dropping tools into energized equipment, incorrectly installing or removing components, or attempting to work on energized equipment without proper procedures. The video frame you see here shows a simulation of a tool being dropped into an energized panel. This is recreating an actual incident that resulted in severe injuries. Loose connections. Connections that loosen over time due to the thermal cycling, vibration, or inadequate initial installation create high resistance paths that generate heat and eventually fail catastrophically. These failures can be particularly difficult to predict because the degradation happens gradually until the final failure is sudden and violent. Incorrectly specified instruments, using instruments or components rated for lower voltage or current than the application, or using components not designed for the specific application environment. Now, here is a critical myth we need to address. Low voltage systems can be just as dangerous as high voltage systems. It's very important. Low voltage system also with dangers at the arc flash methodology because of the short currents divides to resistance at the end of the line. I reviewed incidents where 480 volt systems create more severe arc flash conditions than some medium volt installations. We will see the arc flash labels. You will see the more dangerous the low voltage system, some of the compared to middle voltage installations. The available fault current determined by the transformer size, conductor impedance, and circuit configuration often matters more than the low voltage level. The most important is the panel arrangements in the panel line, the conductors, circuit configurations, and also bus bars. This is why proper arc flash analysis is essential regardless of system voltage. You cannot assess hazard severity based on voltage alone. Let me share some sobering reality about the consequences of arc flash incidents, because understanding the stakes is essential for making appropriate investment decisions in protection. The human cost is obviously paramount. Arc flash injuries are typically severe, third-degree burns covering significant portions of the body, permanent disabilities, psychological trauma. The statistics shown here, the almost one-third of surveyed electrical workers have experienced an arc flash incident. It isn't academic. These are real people in our industry. But let's also discuss the broader impacts, because safety decisions are often made by people who need to understand the complete business case. Financial impact. Arc flash incidents typically results in immediate cost of the hundreds of thousands of dollars, emergency response, medical treatment, accident investigation, operational safety and healthy fines, but the long-term costs are often much higher. litigation that can continue for years, increased insurance premiums, replacements of damaged equipment, and extended downtime while equipment is repaired or replaced. Operational impact. Major arc flash incidents often shut down entire facilities while investigations are conducted and equipment is repaired. I have seen cases where a single arc flash incident resulted in weeks of production downtime, affecting multiple product lines, especially for the chemical sector. Cultural impact. Perhaps most importantly, serious accidents fundamentally change workplace culture. Teams that have experienced a severe arc flash incident often develop either excessive fear that impedes necessary work or dangerous complicacy if they conclude the incident was just bad luck. The bottom line, as our slide states, the cost of prevention is always less than the cost of an incident. This is just a safety slogan. It's economic reality. Proper arc flash analysis, quality personal protective equipment, comprehensive training, and systematic safety procedures represent a fraction of the cost of a single serious incident. This is why we approach arc flash protection as risk management, not just regulatory compliance. Before we dive deep into PPE selection and use, I want to establish a critical principle. PPE should never be your only control measure. This hierarchy of controls, well established in safety engineering, shows PPE at the bottom for good reason. The most effective controls are at the top of this pyramid. Elimination. Can we eliminate the hazard entirely? Sometimes we can de-energize equipment for maintenance. Substitution. Can we replace high hazard activities with lower hazard alternatives? Perhaps using infrared cameras instead of opening electrical panels for inspection. Engineering controls. Can we isolate people from the hazard? Remote operation, arc-resistant switchgear, current limiting fuses all fall into this category. Administrative controls, training, procedures, permits, qualified person requirements. We call it in electrical engineers the LOTO. PPE, personal protective equipment, comes last because it is the least reliable control. It depends on proper selection, correct use, adequate maintenance, and consistent compliance by individual workers. This is why NFPA 70E emphasizes these questions. Before you put on that PPE, what else can you do? This is not just philosophy, it's practical risk management. However, when PPE is necessary, and it often is, it must be selected and used correctly. The remainder of our presentation focuses on how to do exactly that. The foundation of safety arc flash analysis. This is the real ETAP calculation made by me. This brings us to a fundamental principle that underlies everything else we'll discuss. You cannot protect against a hazard you haven't measured. Arc flash analysis is the systematic engineering study that transforms work awareness of electrical hazards into specific quantified incident energy levels at specific working locations. These analyses forms the foundation for all other protection decisions. The screenshot you see here shows typical arc flash analysis software. Also, the other many softwares in this market, like DigSilent and Arc Flash Safety. This isn't just theoretical modeling. This is creating a digital twin of your electrical system that accounts for every significant components: transformers, conductors, protective devices, loads, and their interactions. Why is this so critical? Because arc flash hazards vary dramatically within the same facility. The incident energy at a 480 volt motor control center might be 5 calorie divide centimeter square, while the main electrical room might have areas with 25 calorie divide centimeters square or higher. Without analysis, you are making protection decisions blindly. NFPA 70E requires this analysis for systems operating above 50 volts. It means the touch voltage level in the all international standards. It must be reviewed every 5 years after major system changes. This isn't bureaucratic overhead. Electrical systems are dynamic. Equipment ages, load change, protective devices setting get modified, and new equipment gets added. What was a low hazard location 5 years ago might be high hazard today. The analysis provides two critical outputs: the incident energy level in calorie divided by centimeter square and the arc flash boundary distance. These directly determine PP requirements and safe working procedures. Let me expand on what arc flash analysis actually involves, because understanding the process helps you evaluate the quality and reliability of the results. An arc flash analysis is fundamentally a systematic study to determine both the presence and severity of arc flash hazard throughout your electrical system. It's mandated by standards like NFPA 70E for equipment operating above 50 volts, but the real goal is practical: to determine the specific energy level of a worker could be exposed to during an arc flash event at any given location. In European Union, the similar standards we have EN 50110. We call it the EN standard. These analyses must be updated every 5 years or after major system changes. Why? Because electrical systems evolve. New loads get connected, protective device settings get adjusted, equipment get replaced with different characteristics. A location that was relatively low hazard when your building was new might be experiencing hazardous today. The analysis process involves several sophisticated calculations. Available fault current at each location when the short current occurs. Arc current based on system characteristics. Protective device clearing time. The most important thing is the clearing time. If the arc flash occurs, the current still on the system. That's why we are calculating the clearing time. Incident energy based on arc duration and distance. But here's what makes this particularly complex. Arc behavior doesn't follow simple linear relationships. Small changes in the system configuration can create large changes in incident energy. This is why the analysis requires specialized software and expertise. The key output is converting what-if scenarios into what-is realities. Instead of wondering what might happen if there is an arc flash in the main electrical room, you get specific answers. An arc flash at panel MDP1 will create 18.5 calorie divide centimeter square at 18 inches working distance with an arc flash boundary of 8 feet. This specificity is what enables informed protection decisions. The global standard for calculation. The engineering methodology behind arc flash analysis is primarily based on IEEE 1584, the guide for performing arc flash hazard calculations. This standard represents years of empirical research, including controlled arc flash testing at multiple laboratories. We will look into the empirical research, not for calculation in the theory. What makes IEEE standard particularly valuable is that it's based on real test data, not just theoretical modeling. Researchers created hundreds of arc flash events under controlled conditions measuring actual incident energy levels at various distances and system configurations. The standard provides empirically derived formulas that apply to AC system from 208 volts up to 15,000 volts, covering the vast majority of industrial and commercial electrical systems. These formulas account for factors like system voltage and available fault current, conductor spacing and enclosure type, working distance from potential arc location, protective device characteristic, and clearing times. IEEE standard represents the engineering behind the protection. When we specify PPE requirement based on arc flash analysis, we are not making conservative guesses. We are applying validated engineering methods. The standard is regularly updated as new research becomes available. The most recent revision in 2018 incorporated new understanding of arc behavior. The former one is the 2002, particularly for lower voltage system and different enclosure times. This is why we qualified arc flash analysis requires both specialized software and engineering expertise. It's not just data entry, it requires understanding and the underlying physics and the limitations of calculation methods. Let me walk you through the complete arc flash analysis process, because understanding these steps helps you evaluate the quality of any analysis you receive and understand what information you need to provide. Step 1, data collection. This is absolutely the most critical phase, and it's often where analysis go wrong. We have a saying in engineering, garbage in, garbage out. The accuracy of your entire analysis depends on the quality of your input data. This includes complete electrical one-line diagrams, transformer nameplate data and impedances, conductor types, lengths and routing, protective device types, ratings and actual settings, load data for major equipment, system grounding configuration. I cannot overemphasize how critical accuracy is at this stage. I have seen analyses that were completely invalid because the input data assumed certain protected device settings that didn't match the actual installed settings. Step 2, system modeling. We call it now in digital twin. Using specialized software like ETAP, we create that what's essentially a digital twin of your electrical system. Every transformer, every conductor run, every protective device gets modeled with its specific characteristics. This model must accurately represent not just the equipment nameplate data, but the actual as-built and as-configured system. Step 3, fault current calculations. We calculate available fault current at every significant location, considering both maximum and minimum fault scenarios. Why both? Because different fault current levels can affect arc duration and protective device operation, which directly impacts incident energy. Step 4, protective device coordination. This step determines how quick the protective devices will operate to clear a fault. Faster clearing times mean shorter arc duration and lower incident energy. This is where we see the interaction between arc flash hazard levels and electrical system design, especially if the electrical system inside a generator or rotating motor, this could be dangerous when the arc flash occurs. Step 5, incident energy calculation. Finally, we calculate the actual thermal energy that would be present at typical working distances. This calculation considers arc currents, durations, distance, and the environmental factors. The process flowchart shown here illustrates the systematic approach required. Notice the verification steps. Quality analysis includes multiple checks to ensure results are reasonable and consistent. The end result is specific incident energy values and arc flash boundaries for every significant location in your electrical system. This transforms abstract hazard awareness into specific, actionable protection requirements. Now, let's decode what those analysis results actually mean. The output of arc flash analysis is expressed in calories per square centimeter, calorie divide per square centimeter. But what does this really represent, and why is this particular unit so important? A calorie is a unit of energy specifically. The amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. When we talk about calories per square centimeter, we are describing energy density. How much energy is delivered to each square centimeter of surface area. The critical threshold we work with is 1.2 calorie per square centimeters. This represents the incident energy level that will cause a second-degree burn on unprotected human skin. This isn't theoretical. It is based on medical research into burn injury mechanisms. To put this in perspective, the illustration shows that if you hold a candle flame against your fingertip for 1 second, you'll receive approximately 1.2 calorie per centimeters of energy. Now, imagine that same energy density delivered across your entire torso, face, and hands in a fraction of a second. That's the reality of arc flash exposure without adequate protection. But here's what makes arc flash particularly dangerous. The energy delivery is nearly instantaneous. A candle flame delivers energy slowly enough that you reflexively pull away before serious damage occurs. Arc flash delivers the same energy density in milliseconds, far faster than human reaction time. When we specify PPE requirements, we are essentially asking how much energy can this protective system absorb and dissipate before allowing 1 calorie per square centimeter to reach the worker's skin. This is why I say that the incident energy calculation is literally the difference between a close call and a catastrophe. A location with 15 calories per square centimeter incident energy will cause severe, potentially fatal burns to unprotected workers. The same location with properly selected and worn 25 calories per square centimeter PP will result in no thermal injury. Understanding this energy concept is fundamental to making informed protection decisions. Defining the work area. The arc flash boundary is another critical output from hazard analysis that directly impacts work procedures and PPE requirements. The arc flash boundary is defined as the distance from a potential arc source where the incident energy decreases to 1.2 calorie per square centimeters. The threshold for second-degree burns on unprotected skin. This creates what we call the arc flash protection boundary. The diagram here illustrates this concept clearly. Notice how the incident energy decreases with distance from the arc source. Just like light from a bulb gets dimmer as you move away. The arc flash boundary is where that energy level drops to the injury threshold. Here is the critical safety rule. Anyone crossing the arc flash boundary while equipment is energized must wear appropriate arc-rated PPE. We will use the arc-rated term in the near future common. This isn't a suggestion. It's a fundamental requirement for preventing serious injury. But understanding the boundary concept requires understanding what affects boundary distance. Higher incident energy creates larger boundaries. system modifications that increase available fault current, expand boundaries. Faster protective device operation reduces boundaries. Equipment design and conductor spacing affect boundaries. I have seen arc flash boundaries range from 18 inches for low energy applications to over 35 feet for high energy situations. This isn't something you can estimate or assume. It requires calculation for each specific location. The boundary also defines different zones with different requirements. Arc flash boundary, minimum distance for unprotected persons. Limited approach boundary. Shock protection requirements begin. Restricted approach boundary. Enhanced shock protection required. Prohibited approach boundary. Only qualified persons with specific training and PPE. The key message, know your boundary, respect your boundary. These aren't arbitrary administrative requirements. They are engineered safety distances based on the physics of electrical hazards. Now let's step back and look at how different regions of the world approach arc flash protection. Understanding these differences is crucial for anyone working with international operations, equipment, or standards. We essentially have two primary regulatory philosophies worldwide, but both share the same fundamental goal, protecting workers from the electrical hazards. In North America, we follow NFPA 70E, the standard for electrical safety in the workplace. This represents a quantitative engineering-based approach. NFPA requires specific arc flash hazard analysis and directly links calculating incident energy levels to PPE requirements through a calorie per centimeter square rating system. In Europe and much of the rest of the world, we follow IEC's 61,482, protection against thermal hazards of an electrical arc. This standard takes a somewhat different approach, focusing more on standardized test conditions and classification systems. Both approaches are technically sound, but they can lead to different protection decisions for the same hazard scenario. This creates challenges for multinational companies trying to maintain consistent safety standards across different regions. The key insight here is that these aren't competing standards fighting for market share. They are different engineering approaches to the same fundamental problem. Understanding both approaches helps you make better informed decisions regardless of which regulatory framework applies to your operations. As we work through the specific details of each approach, keep in mind that the goal is always the same, ensuring that workers have adequate protection based on scientifically valid methods. Let's dive deeper into the NFPA approach because understanding its methodology helps you apply it effectively. NFPA requires an arc flash risk assessment for electrical work. This isn't just a checkbox exercise, it's a systematic evaluation that must precede any electrical work activity. The standard directly links calculated incident energy levels expressed in calorie per centimeter square to specific PPE requirements. The standard defines 4 PPE categories, which were formerly called hazard risk categories or HRCs. Each category specifies minimum arc rating requirements for clothing, specific garment combinations required, additional protective equipment needed, face and head protection requirements. What makes NFPA particularly powerful is its quantitative nature. Instead of generic high or low hazard classifications, you get specific energy levels that directly translate to protection requirements. For example, category 1, minimum 4 calorie per centimeter square arc rating. Category 2, minimum 8. Category 3, minimum 25. Category 4, minimum 40 calorie per centimeter square arc rating. But here's a critical point. These are minimum requirements. If your analysis show 15 calorie per centimeter square incident energy, category 2 PP is inadequate. You need garments rated for at least 15 calorie per centimeter square. The standard also includes tables for estimating PPE requirements when detailed analysis isn't available. But these tables are conservative estimates. Site-specific analysis usually provides more accurate and often less restrictive requirements. NFPA 70E represents a data-driven approach to electrical safety. Rather than relying on generic precautions, it provides specific, measurable requirements based on actual hazard levels at specific locations. Let me walk through the NFPA categories in detail because understanding these requirements is essential for proper implementation. Category 1, 4 calorie per square centimeter minimum. Arc-rated long sleeve shirt and pants or arc-rated coverall. Arc-rated face shield or arc flash suit hood. Arc-rated jacket, parka, rainwear, or hard hat liner as needed. Protective equipment, hard hat, safety glasses or goggles, hearing protection, heavy data, duty, leather gloves, leather footwear. This represents the minimum level of arc-rated protection for low energy exposures. Category 2, arc-rated long sleeve shirt and pants or arc-rated coverall, the same. Arc fly suit hood or arc-rated face shield and arc-rated balaclava. Arc-rated jacket, parka, rainwear, or hard hat liner as needed. Same protective equipment as category 1. Category 3, arc-rated long sleeve shirt, arc-rated coverall, arc-rated pants, arc-fly suit jackets, and or arc-fly suit pants, arc-fly suit hood, arc-rated gloves, arc-rated jacket, parka, rainwear, or hard hat liner as needed. Same protective equipment as previous categories. Category 4, arc-rated long sleeve shirt, arc-rated pants, arc-rated coverall, arc-fly suit jacket, and or arc-fly suit pants, arc-fly suit hood, arc-rated gloves, arc-rated jacket, parka, rainwear, or hard hat liner as needed. Notice how the protection becomes more comprehensive at higher categories. This isn't arbitrary. It reflects the increasing severity of potential thermal injury at higher incident energy levels. The key principle, you are matching the armor to the hazard. The protection level must be appropriate for specific energy level workers might be exposed. I'm increasing the speed of the presentation a little bit. The European approach. Now let's examine the IEC approach, which takes a somewhat different path to achieve similar protection goals. The classification of the arc-rated, 2 boxes, and also 2 test methodologies. One is the arc protection class 1, passes at 4 kiloampere test current. The other one, arc protection class 2, APC2, passes at 7 kiloampere test current. It's the test current. It's not just similar with the NFPA standard. This approach is essentially saying for typical low voltage electrical work, these test conditions represent reasonable worst case scenarios. If your PPE passes these tests, it should provide adequate protection for these applications. I'm skipping the open arc test and other test methods. If you have any further question, we will discuss with another webinar. Apples and oranges. The NFPA and the IEC approach is different. This brings us to a critical safety warning that I cannot emphasize strongly enough. APC1 does not equal to category 1 in NFPA. Making this assumption can have fatal consequences. Why? Because an FBA approach is quantitative and site-specific. IEC box test approach is qualitative and the test condition is specific. That's why we call it, you cannot equal apples and oranges. To unifying the metric, I explained it in the former presentation slides. I explained the calorie per square centimeters. Also, I'm skipping these slides. But if you look in the further, the ASTM standard F1959 in the US and the other IEC standards in calorie per square centimeters calculation. The science of protection, technical textiles and garment properties. It's not just clothing, it's engineering protection. The fabric samples you see here represent different approaches to achieving flame resistance and arc protection. We call it FR and AR. Each of these materials has been engineered at the molecular and treatment level to interrupt the combustion process and provide thermal insulation. When we specify arc-rated PPE, we are not just buying work clothes that happen to be fire resistant. We are specifying technical textiles that have been designed, tested, and validated to provide measurable protection against specific energy levels. This engineering approach is what distinguishes modern arc flash PPE from the simple flame-resistant workwear that might have been adequate for basic fire exposure, but provides insufficient protection against the intense thermal energy of arc flash. Understanding the material science helps you make informed decisions about fabric technologies, care requirements, and performance expectations throughout the garment's service life. Arc-rated and flame-resistant. This distinction is absolutely critical for safety, yes, yet it's frequently misunderstood in the field. Let me very explain about the difference between flame resistant and arc-rated materials. Flame resistant materials have two key characteristics. They resist ignition. They are harder to set on fire than ordinary materials. They self-extinguish. When the ignition source is removed, they stop burning on their own. This is important protection against ordinary fire hazards, but it's not sufficient for arc flash protection. Arc-rated materials are flame resistant, plus they have been specifically tested to provide thermal insulation against the instantaneous energy release of an arc flash event. The testing measures how much thermal energy passes through the material during a controlled arc exposure. This is the main critical difference: arc-rated and flame-resistant materials. Here is the critical rule that everyone must understand. All arc-rated clothing is flame-resistant, but not all flame-resistant is arc-rated materials. This is the main difference of the materials. How fabrics get their flame-resistant properties. Understanding how fabrics achieve flame resistance is more important for selecting appropriate materials and understanding care requirements. I can explain with the registered material, the DuPont's Nomex, like aramids, also in the market, being the most well-known example, and Modernix and non-flammable at the molecular level. The flame resistance is built into the chemical structure of the polymer itself. This is the main properties of the flame resistant materials protection. Choosing your fabric technology. The choose between inherent and traded flame resistant technology involves several critical considerations that go beyond initial purchase price. Inherently flame resistant materials, higher initial cost, longer service life, permanent protection, no risk from improper laundering, consistent protection throughout garment life. Treated flame-resistant materials, lower initial cost, shorter service life, protection depends on proper care, can be destroyed by improper laundering. Now, here's the critical vulnerability that makes treated fabrics particularly risky. The flame-resistant properties can be completely destroyed by chlorine bleach, hydrogen peroxide, oxygen bleach, and hard water. As system components, when we talk about arc-rated garments, we are really talking about the protection system, not individual pieces of clothing. Every component must work together to provide comprehensive protection. All components must be flame resistant. Proper fit is crucial. Full coverage is mandatory. This seems obvious, but it's frequently violated. Sleeves must be rolled down, collars must be up, zippers and buttons must be fastened. Any exposed skin is vulnerable to severe burn injury. The key insight, think of arc-rated PPE as an engineering protection system where every component must function correctly for the system to provide its rated protection level. Just as you wouldn't use regular bolts in a high-pressure piping system, you can use regular components in an arc-rated clothing and expect the same protection performance. Proving performance standardized testing methods. Now we move into how we validate all these protection claims through rigorous standardized testing methods. The photograph shows an actual arc test in progress. Notice the intense light, the fireball, the shower of molten particles. This is a controlled recreation of the exact conditions that workers might face during an arc flash incident. When manufacturers claim their garment provides specific levels of arc protection, those claims must be backed by testing according to the recognized international standards. This isn't marketing, it's physics and material science validated through controlled experimentation. ASTM F1959 US and also IC standards. Let me walk through the primary quantitative test method used globally for arc flash clothing. Both ASTM in the States and the IEC in Europe use fundamentally the same approach, exposing fabric samples to a controlled open air electric arc and measuring the thermal energy that passes through the material. The test setup involves creating an electrical arc between electrodes positioned at a specific distance from fabric samples mounted on sensor arrays. Multiple sensors behind each fabric sample measure the heat energy that passes through the material during the arc exposure. The result directly predicts how the material will protect human tissue. If the testing shows that a fabric limits energy transmission to less than the 1.2 calorie per square centimeter, the threshold for second-degree burns, we can confidently predict that the material will prevent burn injury at that energy level. Decoding acronyms: ATPV, EBT, ELIM. The test results produce several metrics that each tell us something different about material performance. Understanding these metrics helps you interpret test data and select appropriate materials. ATPV, arc thermal performance value. EBT, energy break open threshold. Arc rating is always the lower value between ATPV and EBT. Why? Because protection fails when either mechanism fails. If a material has excellent thermal properties, high ATPV, but breaks open at lower energy levels, low EBT, the arc rating is limited by the break open threshold. ELIM, incident energy limit. This is a newer, more conservative European metric that represents the energy level with zero probability of second-degree burn, instead of accepting 50% probability, ELIM aims for no injury risk. The philosophical question becomes, are you comfortable specifying protection based on 50% probability of injury, or do you want zero probability? From a risk management perspective, ELIM provides more conservative protection specification. From a practical perspective, it typically requires higher rated materials with corresponding higher costs. IC box test method. I'm skipping this slide because we already achieved the time limits. And also, if you have further question about the IC standard box test method, we will discuss further on. The final step, now we get the practical application, putting all this technical knowledge to work in real PP selection decisions. The illustration shows the fundamental challenge, matching the right protection to the right person for the right task. This requires integrating hazard analysis, material technology, human factors, and practical workplace considerations. The golden rule of the selections. Here is the fundamental principle that governs all arc flash PP selection decisions. The arc rating of your PP system must be greater than or equal to the calculated incident energy hazard. Never underprotect. If they won't bear it, it doesn't work. This brings us to a critical reality that's often overlooked in technical specification. The best protection in the world is useless if workers don't wear it correctly and consistently. Comfort and fit. Fitting or uncomfortable PP leads to dangerous shortcuts. I have seen accident investigation where workers were severely injured because they had unzipped jackets just for a minute to cool down, or rolled up sleeves because the garments were too long. Each of these creates fatal gaps in protection. Durability. High quality garments that maintain their appearance and performance over time create better user acceptance. Workers develop confidence in equipment that performs consistently. For poor quality garments that show excessive wear, fading, or degradation create the impression that the protection is reliable. Job-specific needs. Many workers face multiple hazards simultaneously. They may need high visibility features for traffic safety, chemical splash resistance for cleaning operations, or moisture protection for outdoor work. The challenge is integrating all these requirements without compromising arc protection. The images here show different workplace scenarios. Each requires thoughtful integration of arc protection with other safety requirements. Compliance through comfort. I use this phrase deliberately. Comfort isn't luxury. It's a component of safety system reliability. Uncomfortable workers find ways to avoid using PPE, modify PPE inappropriately, or use it incorrectly. Head-to-toe protection system, arc flash protection requires a complete head-to-toe approach because the terminology affects the entire body simultaneously. Let me walk through the complete protection systems. Base layers. Never wear malleable synthetics underneath arc-rated clothing. Use 100% of cotton or arc-rated base layers. Head and face. Arc-rated hood or balaclava face shield combination must be used. Hands. Voltage-rated insulating gloves with leather protectors. This requires a system approach combining electrical protection and thermal protection. Voltage-rated insulating gloves protect against electrical shock, while leather protectors provide arc flash protection and mechanical protection for the insulating gloves. Different voltage ratings require different glove thicknesses and testing requirements. The combination must be appropriate for both the electrical hazard and the arc flash incident energy levels. Foot protection. Electrical hazard rated footwear prevents electrical shock through ground contact. The electrical hazard rating ensures the footwear provides electrical insulation between the worker and the ground, which is essential when working around energized electrical equipment. The key concept, protection is a system, not a single garment. Preserving protection, garment care, and maintenance we dive into. How to wash your arc-rated clothing. Do wash separately from non-flame resistant clothing. To turn garments inside out. This reduces abrasion to the outer surface during washing and drying cycles. Surface abrasion can degrade fabric performance and appearance over time. Do use mild detergents. Standard laundry detergents without additives work best. Avoid detergents with built-in fabric softeners, bleach alternatives, or optical brighteners. To follow temperature guidelines, the care label specifies maximum water and drying temperatures that won't damage the fabric or protective treatments. Higher temperatures can cause shrinkage, color loss, or treatment degradation. Cleanliness is the part of the protection. What to avoid at all costs? Never use chlorine bleach or hydrogen peroxide. The chemicals attack the flame-resistant treatments used in the treated flame-resistant fabrics. Never use fabric softener or dryer sheets. Never use starch. Starch is essentially a flammable coating applied to fabric fibers. It completely defeats the flame-resistant properties, can actually increase fire spread rates. The prohibited symbols here represent the most common products that destroy protection. Your 60-second safety checks. Look for holes, tears, or threadbare areas. Check for flammable contamination. Examine frayed collars and cuffs. Test zippers, buttons, and seams. The most important inspection is one you do yourself. While periodic formal inspection by safety personnel are valuable, the daily pre-use inspection by the worker is the most critical quality control step. To say goodbye to garment, the recycling part of the presentation, knowing when to retire protective equipment is as most important as knowing how to use it. The key principle, service life is determined by condition, not age. Retire immediately for holes, rips, or permanent stains. Any contact with bleach means immediate retirement for treated fabrics. When in doubt, take it out of service. Don't risk your life for a worn-out piece of clothing. Closing the loop, end of life, and sustainability. Safety and sustainability go hand in hand. Beyond the landfill, let me walk through modern end-of-life management options that provide both environmental benefits and assurance that retired PPE won't accidentally return to service. Modern recycling programs offer zero landfill solutions for retired arc-rated PPE through a three-tier approach. Tier 1, reuse. Textile in good condition can be repurposed for new textile products. These might include industry wiping cloths, insulation materials, or other applications where flame resistance provides value, but arc rating isn't critical. Tier 2, recycle. Fibers are mechanically shredded and processed in the new materials like building insulation, automotive components, or geotextile for construction applications. Tier 3, recover. Materials that can be reused or mechanically recycled are processed into reuse-derived fuel for energy generation. This captures the energy value while ensuring completing destruction of the original garments, turning old protection into new resources. The last slides of this presentation, the CE certification, CE marking of arc flash protective clothing. Now let's discuss the European certification requirements, which are essential for anyone manufacturing or importing arc flash PP in the European markets. Testing methods. We already shared the information about test methods. CE marking for arc flash protective clothing requires testing according to the IEC open arc and box tests, depending on the intended application and market positioning. CE mark usage. This is required under regulation, the personal protective equipment regulation. The CE marking is just a logo. It's a legal declaration that the product meets essential safety requirements defined in European legislation. Technical file requirements. The manufacturer must compile comprehensive documentation, including product specification, risk assessment, test reports, user instruction, and declaration of conformity. These technical files must be available for regulatory authorities and forms the basis for CE marking. Category 3 PPE requirements. The arc flash protective clothing typically falls under category 3 PPE because it protects against mortal dangers or dangers that can seriously and irreversibly harm health. This requires EU type examination by a notified body like USB certification. The process involves several steps: product testing according to relevant standards, technical file compilation, EU type examination by a notified body, declaration of conformity by the manufacturer, CE marking applied to products. As notified body like USB certification 3038, we see the practical challenges manufacturers face in meeting these requirements. The technical demands are significant, but the process ensures that product placed on the European market provide documented, validated protection levels. This regulatory framework provides end user with confidence that CE market arc flash PPE has been independently evaluated and meets defined performance criteria. Key takeaways and your questions. Let me summarize the critical actions that everyone should take away from today's presentation. Analyze, quantify your specific hazards, select, choose PPE with an arc rating that meets or exceeds the hazards. Inspect, check your gear before every use. Care, launder correctly to preserve protection. Retire, replace damaged or contaminated gear immediately. Thank you for your commitment to safety. Now, we reached the end of our prepared content. I would like to open the floor for your questions. Whether you need clarification on technical aspects we have discussed, guidance on implementing these principles in your specific application, or help with regulatory requirements, I'm here to assist. This has been a comprehensive technical presentation covering everything from the physics of arc flash to practical PP selection and maintenance, and the PDF files will be distributed to all participants following this session. So you'll have the reference materials for future use. Now, if you have any further question, I'm here to assist you. Yes, we have one question already we have. Ricardo asked the question, do you carry these tests in your lab? We carry on the flame resistant testing in our lab, but we don't have already arc flash, open arc, and box tested now. We are planning to establish a new laboratory next year for the arc flash testing. We already exceed our presentation time. If you have any further questions, you can send an email or a quick call to our colleagues. Thanks for your attention and see you later soon. Bye.